반갑습니다. 이번 학기에 최원식 교수님과 함께 여러분에게 현대 물리학 및 실험을 강의하게 된 물리학과의 정재호입니다. 이번 주에 제가 학회에 참석 중이라서 오리엔테이션에 함께하지 못해서 미안하게 생각하고요. 이번 첫 시간, 첫 주 강의는 블랙보드를 활용해서 동영상 강의로 제작했습니다. 우리가 교과서로 사용하게 될 이 톤튼 앤 렉스의 Modern Physics for Engineers 이 책의 첫 장은 새로운 물리를 가르치는 부분이 아니고요. 여러분이 기존에 배웠던 현대물리 이전의 고전물리 부분을 한번 리뷰해보는 부분입니다. 따라서 동영상 강의로 제작하기에 적절하지 않나 한번 생각이 되고요. 그리고 알겠지만 이번 강의는 영강입니다. 그래서 앞으로 모든 강의는 다 영어로 진행하게 될 테고요. 물론 여러분이 너무 어렵지 않도록 적절히 한글을 섞어갈 것입니다. 그리고 이 첫 부분에 이 강좌를 소개하는 부분은 보다 여러분들이 이해하기 쉽도록 한글로 제작하도록 하겠습니다. 자, 강의를 시작하기 전에 한번 교과서 전체를 살펴보도록 하겠습니다. 이 교과서는 총 16개의 챕터로 이루어져 있는데 그 중에서 이번 강의에서는 약 절반 정도를 공부하게 될 것입니다. 지금 이 박스로 채워진 부분이 이번 강의에서 커버할 부분이라고 생각되고요. 자, 이 부분들은 크게 상대성 이론과 양자 물리로 나눌 수가 있는데요. 이 두 가지는 현대 물리의 가장 중요한 두 축이라고 할 수 있습니다. 예전에는 역학 2에서 상대성 이론을 배웠었는데 지금은 역학이 한 학기 과목이 되면서 아마 이번 강좌가 상대성 이론을 가르치는 첫 시간이 되지 않나 싶네요. 또 양자 역학은 이번 학기에 과목을 따로 듣는 학생들이 많이 있을 텐데 사실 이 현대물리 과목을 한 학기 먼저 듣는 것이 보다 바람직하긴 합니다. 하지만 학과 강좌 배치의 제약으로 인해서 같은 학기에 된 것임을 이해하시면 되겠습니다. 그리고 8장부터 나오는 내용들은 원자물리, 통계물리, 현대광학, 고체물리, 핵 및 입자물리 등 이러한 양자물리로 인해서 발전하게 된 여러 학문에 해당하고 여러분들이 4학년 때 듣게 되는 여러 과목들과 연결이 되게 됩니다. 그래서 이번 학기에 많은 부분을 강의할 시간은 없겠지만 관심 있는 사람들은 각자 스스로 공부해 보는 것도 좋을 것입니다. 자, 이제 다음 페이지부터는 강의를 시작하게 되므로 영어로 강의를 하도록 하겠습니다. Now let's begin the lecture of chapter 1. What we study in this course is modern physics. What is modern physics? In order to understand what modern physics is, we will first have to understand what physics is and then think about what classical physics is as opposed to modern physics. According to Wikipedia.com, the physics is described as the general analysis of nature conducted in order to understand how the universe behaves. Basically, what it means is that physics is the study of everything around us, what the universe is, and how the universe is. The word physics comes from physike in Greek, which means the knowledge of nature. In trying to understand nature, we physicists use two complementary approaches. One is the experimental observation, and the other is the mathematical theory. The two most famous scientists in these two areas until 19th century are probably Galilei for experimental observation and Newton for mathematical theory. The physics until 19th century is based upon their works, which we call classical physics. So now, what is modern physics then? Modern physics is defined as the physics of the 20th century and onwards. If you say modern, it may sound like something new, but here we realize that modern physics is not new anymore because it is already more than 100 years old. Nevertheless, what it teaches us is quite different from what the classical physics has told us. For example, in relativity, the space and time are no longer separate, but in fact are entangled with each other. Another equally important modern physics comes from quantum mechanics, which is based upon the puzzling idea of waves and particles being the same. As we will see throughout the course, it does not mean classical physics has been wrong. It only means that scientists have been wrong to believe the classical physics can explain everything. Now we know that classical physics explains only limited part of the universe, and modern physics can describe the universe in much wider context. Now let's see what the world was like just before the birth of modern physics. Europe has been undergone tremendous changes since the scientific revolution that spanned between 16th and 18th centuries. By 19th century, European intellectuals have figured out how they can transform the abstract natural science into practically beneficial technologies. Their success was highlighted not only by the Industrial Revolution of the late 18th and early 19th centuries, but also by the imperialism or colonialism of the same period. I'm not going to read what is written on the slide, but you can easily notice that the reason why Europeans could make such a progress and dominate the world was all based on the classical physics, which allowed them to move things and people farther and faster, particularly commodities, guns, and soldiers. For example, how this steam-powered ship works is described by the thermodynamics that you have learned in general physics. Without it, they could not have sent a large number of soldiers and big armies to faraway places like Africa or Asia, and subsequently bring back large amount of commodities for trade. During this process, mechanics was important in running machines, and electromagnetism was essential in making long-distance communications. The science and technologies of Europe already spread to North America, which was in fact a part of European culture, and China and Japan were just beginning to learn European science. What was happening in Korean Peninsula in the meantime is not what we are particularly proud of, because Joseon Dynasty was still implementing the policy of refusing any foreign influence other than from China. Therefore, whether you like it or not, the history of classical physics is 100% European thing. So please bear that in mind. Now let's come back to physics and quickly review the classical physics established as of late 19th century, the time just before the modern physics was born. The physics until 19th century was dominated by the name Isaac Newton. His mathematical laws of mechanics beautifully explained how motions of particles with mass changes under applied force, whether the particle is on the earth or far away in space or heaven, if you like. There are three laws of motion, as you already know very well. The first law describes the motion with zero external force, the second law with non-zero net force, and the third law regarding interactions between two or more particles. While Newton's laws were formulated around forces, many other physicists contributed by introducing important concepts like energy or momentum. For instance, the kinetic energy was first introduced by Leibniz and later recalibrated with the factor half by Coriolis, which allowed the establishment of conservation of mechanical energy. The linear momentum, which is a different form of quantity of motion, also has a conservation law. In fact, the conservation of linear momentum has been implied in Newton's third law. There is another conservation law for angular momentum, which is the rotational version of the momentum conservation, and it is in fact equivalent to the conservation of linear momentum. We also have to include the conservation of charge asserted by Benjamin Franklin as one of important classical conservation laws, although it is not mechanics. Physicists eventually figured out that the concept of energy was not limited to mechanics, but also could be extended to the area of thermodynamics, dealing with heat or temperature. In doing so, the study of gas proved to be crucial. Many scientists like Boyle, Shuttle, Gay-Lussac investigated the pressure volume or volume temperature relations of gases, which were later combined by Clapeyron to formulate the ideal gas law. The proportionality constant in this ideal gas law equation includes two important numerical values. One is the gas constant and the other the Avogadro's constant. Later, it required the geniuses of Maxwell and Boltzmann to apply Newton's mechanics to the theory describing properties of gas. The outcome was that the temperature of the gas is in fact ascribed to the kinetic energies of gas molecules. This discovery was absolutely fundamental because it established the direct connection between thermal and kinetic energies. What comes next are the laws of thermodynamics. Thermodynamics is the physics dealing with heat, work, and energy, and it explains whether an energy process can or cannot take place. The introduction of entropy is one of the most important contributions not only to the science, but also to the academy in general. There are three laws of thermodynamics. The first law is essentially the conservation of energy, including thermal energy and work. The second law can be stated in many different ways, and probably the most popular way is that it is impossible to make a perfect engine. This is where the concept of entropy was introduced. These two laws were built based upon works by Carnot, Clausius, and Thomson, and were clearly stated later by Gibbs. The third law was in fact discovered in the 20th century, stating that the entropy of a perfect crystal at absolute 0 Kelvin is exactly equal to 0. The other pillar of classical physics, which is equally important to mechanics, was electromagnetism. Earlier works by Coulomb established the electrostatic force, which was later reinterpreted by Faraday as the electric field. The concept of field was also used by Biot-Savart to understand magnetism. Later, Weber and Kohlrausch measured the product of the electric permittivity and magnetic permeability constants, which were understood as the ratio of electromagnetic and electrostatic units of charge back then. Finally, it was James Clerk Maxwell who combined them all in his famous four equations. He also realized that the speed of light is very close to the value measured earlier by Weber and Kohlrausch. Therefore, the speed of light is in fact the speed of waves in his equations, from which he established the concept of electromagnetic waves. On the other hand, Lorentz force law, which combined the Coulomb force with the force due to magnetic field, was established relatively late, very close to the turn of the century. As we have seen so far, classical physics was built around the concepts of either particles or waves. Particles are entities with small volume and non-zero mass, and their motions are well understood by mechanics. In contrast, waves are extended over very large space and time, and can transfer energy but not the mass. Although Newton mechanics helped to formulate the wave equations, electromagnetic waves were considered to have nothing to do with particles. Since the ancient times, human beings were always intrigued by the question of light. Newton said it must be streams of particles because he observed the shadows were very sharp, and he thought he could explain reflection and refraction based on particle picture. In contrast, many others thought light was a wave. So who was correct? Finally, the famous Young's double-slit experiment on sunlight confirmed the wave nature of light. It was then followed by Maxwell's proposition of light to be electromagnetic waves and Hertz's observation of electromagnetic waves far outside the visible range. In the 19th centuries, waves were visualized as disturbances of certain media, like water or guitar strings. Since the light was believed to be waves, the scientists had to assume that there must be a medium through which light waves propagate, and they called it ether. Another important idea developing quickly at the turn of the century was the atomic view of matter. The atoms being the basic building blocks of matter had originally been proposed by Democritus in classical Greece. At the beginning of 19th century, the law of definite proportions were proposed by chemists like Proust and Dalton. Then Avogadro proposed the existence of molecules that consist of one or more atoms, and Brown observed the famous Brownian motion, which were later explained by Einstein as the evidence of atom. Nevertheless, many physicists refused to accept the existence of atom. For instance, Ernst Mach said that if you cannot see it, then it should not be there. So there were certainly unresolved issues between scientists. In spite of some disagreements, scientists in the late 19th century were confident about the success of physics, not only by its mathematical beauty, but also by the economic prosperity that science and technology have brought in. They thought they already understood the physical world almost perfectly. Around that time, Max Planck was said to be a gifted young man in both music and science. Music was also very big in late 19th century Europe. When he decided to choose science over music for his future career, the Munich physics professor Philipp von Jolly advised him against it, saying, "In this field, almost everything is already discovered, and all that remains is to fill a few holes." From this remark, you can guess a lot about feelings of 19th century scientists. It is said that Planck replied, "It is not that he wished to discover new things, but only to understand the known fundamentals of the field, and the rest is history." Now let's close the lecture by summarizing the unresolved questions as of 1895. Just as we have seen, the atomic theory of matter was still controversial. It was not universally accepted, and even among scientists who accepted it, more questions were raised. If atoms indeed exist, are they the smallest, or can they be divided even smaller? And how are they arranged in matter? At the same time, there were three unresolved fundamental problems regarding nature of light. First one was the existence of medium for light, or ether. The second was about the speed of light coming from Maxwell's equations. If the speed of light is obtained by two experimental constants, then in the moving frame where relative speed is added to the speed of light, do these constants change, and thus the Maxwell's equation should be rewritten? The third question was their inability to explain the distribution of radiation from hot matter by using knowledge of classical physics. This last one may sound rather minor, but later it played the pivotal role in the development of modern physics. Additionally, there were several discoveries from fast-developing experimental physics which complicated the whole picture. For instance, X-rays were discovered, and physicists were not sure whether it is an electromagnetic wave or completely new type of energy flux. Radioactivity was also discovered a year later, which puzzled physicists why atoms spontaneously emit X-rays. When electrons were discovered, scientists realized they were something smaller than atoms, but not sure what they were. In addition, Zeeman discovered that spectral lines of non-magnetic atoms changed under the magnetic field, which he had no way to explain. Likewise, contrary to the Munich professor's confidence, there were a whole array of fundamental questions waiting for the new physics. So, welcome to the 20th century and the chapter 2 next week. 자, 그럼 지금까지 강의를 듣느라 수고가 많았습니다. 이것으로 첫 주 동영상 강의를 마치고요. 다음 주에는 강의실에서 제2장 Special Theory of Relativity, 특수 상대성 이론을 내용으로 함께 공부해 보도록 하겠습니다. 감사합니다.